Hello everyone. Let's start today's session with a simple question. Why does sugar water not conduct electricity, but salty water lights up a bulb instantly in the lab? The answer lies in the fascinating concept of ionic equilibrium. Ionic equilibrium occurs in solutions where ions are actively taking part in reversible reactions. For example, in the equation Fe3 plus ion in aqueous solution plus Sca minus ion in aqueous solution gives the complex ion Fe2 plus in aqueous solution. This balance of ions and molecules defines ionic equilibrium. Non-electrolytes such as sugar never dissociate, while electrolytes dissociate into ions, enabling conductivity. Weak electrolytes, in particular, show equilibrium between their ionized and unionized forms. That's the playground of ionic equilibrium, and it's what we'll explore today.
Now, let's look closer at electrolytes. Strong electrolytes, such as sodium chloride or hydrochloric acid, ionize almost completely in water, nearly 100% dissociation. This means no unionized molecules are left. Weak electrolytes, on the other hand, like acetic acid or ammonium hydroxide, only partially dissociate. Here, equilibrium is set up between ions and unionized molecules. For example, CH3COOH in water exists as both CH3COOH molecules and CH3COO- plus H plus ions. The degree of ionization becomes a crucial property. The higher the ionization, the stronger the conductivity. That's why a beaker of sodium chloride solution glows brightly with a lamp, while acetic acid only gives a faint current. So, what exactly is ionic equilibrium? It's the state where the rate of ionization equals the rate of recombination. For a weak electrolyte like acetic acid, Ha dissociates into H plus and A minus ions, but at the same time, some of those ions recombine back to form Ha molecules. At equilibrium, these two rates balance each other. Acids, bases, and salts all fall into this framework. The strength of an electrolyte can be defined through its ionization constant. The higher the value, the stronger the electrolyte. In this way, ionic equilibrium provides the mathematical and conceptual base for understanding pH, buffers, solubility, and more. Let's go back in time to Michael Faraday, who gave us a brilliant classification. He divided substances into electrolytes and non-electrolytes. Electrolytes are those that conduct electricity in aqueous solutions, like sodium chloride, while non-electrolytes such as sugar or ethanol do not. Faraday further divided electrolytes into strong and weak types. Strong electrolytes ionize almost completely. Think of hydrochloric acid, nitric acid, or sodium hydroxide. Weak electrolytes ionize only partially. Examples include acetic acid, carbonic acid, or ammonium hydroxide. This classification still forms the foundation of how we approach ionic equilibrium today. Now, where does this concept matter in the real world? Ionic equilibrium is used in calculating the pH of weak acids and bases, predicting solubility through solubility product, and designing buffer solutions. It's central to acid-base titrations and to understanding why certain reactions in biology, like enzyme activity, depend on pH. Industrially, ionic equilibrium guides processes like water treatment, food chemistry, and pharmaceuticals. A key relation here is the Henderson-Hasselbalch equation. pH equals pKa plus log of concentration of conjugate base divided by concentration of acid. This equation is applied in buffer design, blood chemistry, and countless lab applications. So to wrap up, let's summarize. Ionic equilibrium describes the balance between ionization and recombination in solutions. Strong electrolytes undergo nearly 100% ionization, while weak electrolytes set up a true equilibrium between ions and molecules. Conductivity becomes a practical measure of ionic strength. Acids, bases, and salts act as electrolytes, and their equilibrium behavior explains everything from the glow of a lamp in a salt solution to the stability of biological buffers in our blood. Ionic equilibrium isn't just a classroom topic. It's the hidden control system behind chemistry in life, labs, and industries. I hope this discussion helped you see ionic equilibrium as not just equations, but as the invisible chemistry of living and non-living systems. See you in the next session with another exciting concept.